Hello, beautiful primates. Today, we're going to discuss a simple statistical test that you can use to find if there is a mathematical difference between two groups of specimens. This is the good old-fashioned t-test. Now, I'm going to show you a way to arrive at the t-statistic that is a bit convoluted and long and has some extra steps in it. However, while we could take shortcuts to those answers, I think it's important to take a step-by-step approach to it and conceptually wrap our heads around the math that's going into this. So if you have spent a lot of time working with spreadsheets already, we're not going to get too far in before you realize there are some shortcuts we could take, some functions we could use, and we could eliminate some of these steps. However, I think it's important to take a step-by-step approach through the process of calculating a t-statistic by hand. That way you can conceptually understand the math that is happening. Now there is a little math here, and I'll admit when I first started learning about statistics this was pretty intimidating, but it helps to draw some pictures. So we're going to draw some pictures on our way through it, and we're going to take a step-by-step approach through building up to that statistic, and along the way we're going to learn some spreadsheet magic. So I like to think of a spreadsheet as it's a box of tools. There's all kinds of tools in that box that you can use to build all kinds of things with. It's kind of like a blank slate. So here, I've taken the liberty of filling in the data that I collected from my Drosophila fly experiment. I only have two groups to compare in this particular instance because I didn't end up with any viable males from my test cross. So I'm just comparing females of my control group to females of my experimental group. Now, I've recorded my times into my spreadsheet here as minutes and seconds because that's what the little timer on my lab bench read out in. However, this is not useful in a spreadsheet. We can't really do calculations with times written this way. We could convert them to decimal times by, we could convert the seconds to like hundredths of a minute, but that math is a little bit more convoluted. But there's another way that we can shortcut our way to this, and we can convert minutes and seconds to seconds. And fortunately, there's a nice little tool in our spreadsheet that allows us to do this. So the first thing I want to do is click on the header of this column here, this second column, and make a little more space. And so I'm going to click on the header of that column at the top, highlight that way it highlights the whole column. I'll right click up there and I will select insert one column left, and I will do that 2 more times. Okay. And I'm going to go ahead and title these columns minutes and seconds and total seconds. Okay, we're going to make some magic happen here. So copy and paste are our best friends. Let's go ahead and copy these and paste in another set of them over here for my other group. Okay, so next step, we're going to use one of the built-in functions of our spreadsheet called split. And so anytime we're putting in a function in a cell, we start with the equal sign and we start typing the name of that function. And that is going to be p split. Okay, we hit enter, it'll complete it. Now notice there are some parameters that it asks for. Parameters in these brackets are optional, and parameters that are not optional. So the spreadsheet's going to expect something for that parameter. All right, so the first parameter is text. That's an input value that we're going to give this function, and we're going to take this. So what we're doing is we're treating this as text, and we're going to split it right in the middle. So the next one is then we'll have our comma, and then the delimiter. Well, what's delimiting what we want to split is that colon. Okay, so we'll put in colon in quote marks, and that's good enough. We don't need those other parameters for this. And we'll hit enter. And this is why we made the extra column. So it takes the first part of the split and puts it into one column and the second part into a second column. And however many values you're splitting, that's how many columns you need. All right, and then the next magic trick we can do with a spreadsheet is we can highlight this cell, and instead of having to type that in all the way down, we can repeat it. So if we hover our cursor right here over this little square at the bottom right, and our cursor turns to a little plus sign, that might be a little hard to see, but when it turns to a plus sign, that's when you can click and drag down the column, and it'll repeat exactly what you did, but in the correct space. So you can see all of our times are nicely split into a minute column and a second column. And then by now, what we're doing, you should suspect, is we're going to put another formula in here, and it thinks we want to sum these up. So the computer doesn't always know what we want, but no, not quite. So what we want to do is take, and remember parentheses. So we want to take the number of seconds and then the number of minutes times 60. So we'll take this cell times 60, and then we'll add this cell to it. Close the parentheses. That's good. And all right. And now it knows what we want, and so we can just hit Control Enter, and off we go. And so now we have total seconds. And that's a number we can work with. That's a number we can calculate with and crunch some statistics with. All right, now we can duplicate this right over here on the other side for our other group. We can actually copy this and come over here and paste it, and it will correctly split these times, because what it did is it copied our formulas. And you can see it copied the correct formula over, just shifted the cells over. All right, two things. I always forget to do this right off the bat, but we want to name things to keep track of what we're doing. So give that file a name. Otherwise, you'll have a folder full of stuff called untitled spreadsheet. So I usually try to give things my name and then whatever class I'm working with in this case, and sometimes a section number if you have one, but there was only one section of this class. And then this is my second fly cross of the semester, so I will call that cross 2. Okay, and then I'm going to name this sheet too. So if we go down here to this bottom tab and you just double click on that name, you can change the name of the sheet, and I'm just going to call this my time calcs. You can call it whatever you want, but it helps to keep track when you start getting multiple sheets going, which one you want to click through instead of, well, was I on 2 or 3 or 7 or 14? I don't remember. So right now, what I'd really like to do is get some of this cruft out of my way. So for example, I don't need any of this stuff. I don't need the minutes and seconds split out. The only information I need for each group is the total seconds. So I want to just get rid of all of this. So before I go crazy and delete anything, what I like to do is I like to just make an extra copy of that sheet. So in case I mess anything up, I haven't wiped out all of my data. So down here at the bottom, I can right click on the name of my tab and I can duplicate. Now I have an extra copy of time calcs. Now, since all I want is the total seconds, I'm going to take my title, I'm going to cut, Control X, and I'm going to paste that over here. I'm going to do the same thing here and move it over here. All right, now I can get rid of these 3 whole columns. Delete columns B through D. Yes, that's what I want to do. Uh-oh, something went wrong. My total seconds are gone. So when you see a ref error, reference does not exist. So what happened here was, remember we did a calculation to arrive at this number. We lost the numbers we did the calculation from. So let's back up a step. We'll use our good friend Control Z to back up a step, right? So we lost all the numbers that we calculated this value from with this formula. So there's a quick trick to take care of this. And so you can copy these values. You can copy, and then you're just going to paste the same values right back in. But instead of a regular Control V paste, you're going to go to Paste Special and Values Only. So you don't want the formulas now. And you can also use that Control Shift V shortcut. So we're going to paste our values only back in here. So now we can highlight these columns and we can delete them, and our times are still here. So we'll go ahead and do the same thing to this other column. We'll copy, and then we'll paste special, values only. And notice there's a few other options here that may be useful at different times. Values only, and then we will delete these columns. Okay, so now we have the numbers that we need in the format that we need them. All right, so let's go ahead and spread these columns out a little more. All right, so when you're working with spreadsheets, don't be afraid to add some blank columns or blank rows in between to make some space for notes you need to make or whatever. And from here on out, I'm going to number all of my steps so that so we don't get lost. So here, I'm going to say step 1. We're going to calculate the mean of each of these values. So we'll start with our equals, and we'll start typing average. And the spreadsheet is pretty smart, and it knows we want an average of all these values in this column. We can just hit enter, and ta-da, we're good. And we can take this value, or this formula, we can copy it and paste it over here. So now we have our mean values, and they do look different. 603 versus 726.8. So we can write this into our paper and we're done here, right? Not so fast. We need to have a word about variance. So this is just for demonstration purposes. You don't have to do this as part of your analysis, but I went ahead and made histograms for each of these sets of values. So I have a histogram for my control group, which is marked ATTP40, and a histogram for my experimental group, which is marked GPDH. So in the histogram, these values on the x-axis represent buckets. And these are 50-second increments, buckets. And then the y-axis represents how many values we had in our distribution of scores that were in that bucket. So for example, this one here, this bar here, represents one count in the 300 to 350 seconds bucket. This one has 2 in the 350 to 400. And so we've done that for both sets of scores, and we can look and see that maybe these are a little bit different, right? The GPDH ones seem to be distributed a little farther to the right, a little bit longer to wake up from that chill coma recovery procedure. But we can also see that out here on the far right side of each of these graphs, there's an outlier. There was one fly that just took longer to wake up than all the rest, and maybe that's an outlier and maybe that's not. But that's not usually an arbitrary decision you make. It's a mathematical decision that you make, and maybe you'll talk about that in class. But we'll come back to that idea later. So the point to carry away from this is these two distributions of scores visually look a little bit different, but are they actually mathematically significantly different? And that's where we're going to get into the magic of the t-test. And for that, we need to cut to a quick commercial break. So first things first, instead of that sort of messy bar graph kind of a thing, I'm going to draw a shape that hopefully you're familiar with by this point. And that's the bell curve or the Gaussian curve. And what this represents is a normal distribution of data. And all that normal really means, and we should put this in quote marks, honestly, because normal just has a specific meaning here, meaning that there's about, or that the data are evenly distributed on either side of the mean, and that they happen to be kind of clustered closer to the mean than further away from it. So, thinking back to our histograms in the last frame, we have distributions that appear to overlap a little bit, right? So for our green set of data here, that's our mean. And for our yellow set of data, here's our mean. And we can calculate very easily the difference between these 2 points, right? We've already calculated the means in our spreadsheet, and we can very easily calculate the difference between them, like so. So I've labeled the cell here for the mean difference, and we can take this value and subtract the other value. Pretty straightforward, right? So this will just be equal to this minus this, whoops, minus this, hit enter. Okay, well, we don't want to, or at least I don't want a negative value for my calculations, and this is why it doesn't necessarily matter which one you subtract from which. The difference is the same. So what we'll do is we'll go ahead and select that cell, and we'll throw in the absolute value function. And that'll just give us the absolute value of whatever is in that, so we always end up with a positive value, and we'll go from there. All right, well, that's our mean difference. So back to here, that's essentially this right here, okay? And so that is our mean difference. But that doesn't necessarily tell us enough yet, because let's think about this, right? Let me paint you 2 different pictures real quick. So let's say that we have some really widely distributed data with a lot of variance. And that's going to give us a distribution that looks like this. So say that here's the mean of our data, and our data is just really spread out across this whatever's on our x-axis. Versus we might see a distribution that is really much more vertically shaped like this. And so what this indicates is that our data are much more tightly clustered around the mean, right? So we have a tighter distribution versus a wider one. And this is what variance refers to, okay? So the green one here has a high variance or wide spread in that distribution. And the red one has a narrow distribution that is low variance. Now our standard measure of variance that we use is the standard deviation. So what is standard deviation? Well, in words, it's the average distance between each sample and the mean. Well, the mean is represented here by this dashed line through the center of the distribution. And then we have our random samples that we've taken from our population or from our sample. And what we want to know is what is the distance between each one of these samples and the mean. So for example, from the mean, we can measure the distance to this sample, and that has a value. And then this one has a distance from the mean, and that has a value. And so we do that with all of our samples. We add all that up, and then we take an average of it. Now, one important fact to bear in mind is that when we're talking about standard deviations, we can count numbers of these. So let's say, for example, that our standard deviation in this case is equal to 5, just for giggles. And let's say that 5 is here on our x-axis, and this is -5. So 1 sigma, or 1 standard deviation, is at 5, and typically in normally distributed data, we will find roughly 67% of all of our values inside of that first standard deviation range. So we can call this range here and this range here. So this is to -1 sigma, and this is positive 1 sigma, or 1 standard deviation, right? All right, so standard deviation is good to know, but put a pin in that for a minute and we'll come back to it. There's another thing we need to work out. So let's say we have our two distributions of values and we have a difference between them, which is our mean difference. We also know that, like down here, there's some overlap. And we kind of expect that, but maybe not. So if we're going to find out if these are actually different, we have to practically compare these two. So we have to consider their difference in means as well as their variance. And to do that, we're going to calculate the t-statistic. So what is t? So t is equal to the difference in means. And I like to write my math out in whole words sometimes because it helps me to remember what's going on instead of like assigning letters to things. That's the difference in means over the estimated standard error. All right, well, we already have the difference in means, right? But we don't have the estimated standard error yet. And so we're going to have to calculate that. Now that's going to take us a few more steps. Okay, now this is going to go off in the weeds just a little bit for a second, but I promise this will make sense in a minute. All right, so I don't want to throw too much algebraic notation at you guys, so I'm going to kind of write out the math in words and abbreviations a little bit. So we need to find out what our estimated standard error is. And I'm not going to explain where we get all of this. That's in the scope of like a regular statistics class. But the estimated standard error is equal to the pooled variance, and I'll come back to what that is in a moment, the pooled variance over N1 plus the pooled variance over N2. All right, so what did these represent? Now the pooled variance, all that is equal to is the variance from each group divided by the number in that group, and we add those up. So that's going to be the variance from group 1 plus the variance from group 2, and that's all going to be divided by the degrees of freedom from group 1 plus the degrees of freedom from group 2. Now I haven't explained degrees of freedom yet, or variance. We're going to get to that. So I'm basically working backwards through the math steps here. So remember that our t-statistic is equal to the mean difference divided by the estimated standard error. So we're working backwards to get what we need. So we have our formula for estimated standard error here. We need the pooled variance. This is the formula for pooled variance. And n here just refers to the number of samples. So in that case, so n is just the number of samples here, and we had 15. So we'll add a few calculations to our spreadsheet to help start making some sense of this. Degrees of freedom is n minus 1. And I'm not going to go into the whole lecture on why we use degrees of freedom for samples. The important thing to remember is that you use, typically we use n as the sample number in a population, and we use degrees of freedom for a sample, and that's n minus 1. Now we're going to go to step 2. Now we're going to go ahead and calculate our n for our samples. Now we know we have 15 samples here, sure, but something might change later. Or maybe we want to remove a value to see what it looks like without a potential outlier. Or maybe we're working on a different project and have a huge number of values and we don't want to count them all. So we'll use a built-in function of the spreadsheet to do that for us. So our n, which is our number of samples, and we'll use a built-in function called count. So we'll go equals count. All right, now it wants to count over here in column A, but we don't want that. We'll just drag and highlight here, hit enter, okay. and it agrees with us. So we're going to go ahead and do a copy and paste this over here. All right, step 3, we might as well go ahead and calculate our degrees of freedom because this is a really easy one to calculate. So step 3, our degrees of freedom, which we abbreviate as DF, and this is always n minus 1. And because DF is always equal to n minus 1, fairly straightforward, we do an equals, open parentheses, this value, minus 1, close the parentheses, hit enter. Okay, that's correct. We will copy and paste over here. All right, the next thing we need to calculate is the variance. And I'm going to go ahead and give myself one more column here just to give myself a little space. So this column will be the variance, and I'm going to go ahead and number this with step 4. All right, so I've come up top here, and I've labeled step 4 as, you'll see this, x minus mean squared. And the reason we square these values is, remember that some of these values are going to be on the left side of the mean and some are going to be on the right. And the negatives will cancel the positives out. So that's why we square all the values, makes them all positive, and then we can take the square root later to get the difference. And then so here we'll just take this, we'll do an equals, and then what we want is the difference between the mean and our x value. Let's actually just do that right here. Let's escape out of this, and we'll put our x right here. That way we know, right? So this is our x. We'll take this, copy, paste. All right. So we'll do an equals, and then x minus mean. All right, so this is our x value. We'll do a minus, and then the mean value is down here. That's this 603. And we close parentheses. Now we're not quite done yet, because if we copy this formula all the way down this column, what the spreadsheet is going to try to do is take this C19 value right here and drop it down to C20, C21, and so on. So we need to lock this cell. We want it to always take that exact cell. So we're going to do a $, C, $19. Now the dollar in front of the C locks the column. The dollar in front of the number locks the row. So we've locked the column and the row. If we only had the $sign on the C, then we'd only be locking the column and not the row. And there's times when we want to do that. There's times when we only want to lock the row. In this case, we only want the one value, so we want to lock it down to the single cell. And so we're not quite done yet. That just gives us the difference with the mean, and now we're going to square it. So we can use the little caret symbol. 2, and now it's squared. Okay, now we want to copy that formula down the column. And now we have all of our variances. And what we'll go ahead and do is we'll copy and then paste that over here on this side too. So we have the same thing. All right, so that's step 4. Step 5, we are going to need a sum of all of these squared deviations. So we'll do that. And I'm going to go ahead and put that in this column to kind of keep things organized. And so that's going to be an equals sum, and we're just going to add up numbers. And we want to add all of these deviations, these squared deviations. All right, pretty good size number there. We'll copy and we'll paste over here as well. And while we're at it, we should go ahead and calculate the standard deviation. Now there is a built-in function in a spreadsheet to calculate standard deviation of a range of values, but we can also calculate it by hand, and that's fairly straightforward. It is the square root, and we'd start typing SQ square root, and that is going to be the square root of this, the sum of squared deviations, divided by the degrees of freedom. And you don't have to memorize this or remember it. You can always Google the formula for standard deviation whenever you need it. This is just how you put it into a spreadsheet and use that sort of thing when you need it. All right, so we have a standard deviation here, And we'll go ahead and copy paste it over for the other set of data. All right, so we have our standard deviations now for each set of data. And that really just tells us the average distance, again, the average distance of any one of our x values from the mean of that set of values. All right, and so the next thing we want to calculate is that pooled variance. So I'm skipping a line here just to break things up a little bit, not for any particular reason. We'll put in our pooled variance, which we remember is we add the sum of squared deviations and then divide that by the total of the degrees of freedom. All right, so I've labeled this column as totals over here now. Okay, pooled variance. So pooled variance is equal to, remember we add up our sums of squared deviations for both groups. And so that's this one plus this one. And then we're going to divide that by adding up the degrees of freedom. So that's this one plus this one. And then the last value that we need to calculate before we can get to our t-statistic is that estimated standard error. So we remember that the estimated standard error is equal to the square root of the pooled variance divided by n1 plus the pooled variance divided by n2. And it's the same number in both cases. So divided by n1, so we come back here, that's our number of samples. And we're going to have to add some more parentheses. So this is going to be plus, and then our pooled variance again, divided by n2. Now if this seems like a little extra step, maybe it is, but maybe our numbers change later, so that's why we do it this way. Okay, so that's our estimated standard error. So now we have everything we need to compute our t-statistic. So which remember again is our mean difference, which we have here now, divided by the estimated standard error. And that's that. Okay, now we have a t-statistic. We're done, right? Not quite. We need a little bit more information first. So in the olden days, we used to have to look up in statistical tables, like these, to find out what our critical value was. And we would find out, we would look up according to our alpha value, which is the cutoff for our experiment. We might set our alpha value at 0.05 or 0.01. That's our critical value. And we have to surpass that critical value in order to have statistical significance. So for example, if our alpha value is 0.05, that means that we must get a value for our t-statistic that we should get less than 5% of the time on a random sample. Here, as it just so happens, the spreadsheet has a built-in function that allows us to look up that critical value in a statistical table without having to actually look at a table. All right, so what is our critical value at alpha equals 0.05? So we have a function, and that function is tinv, T-I-N-V, the inverse t-distribution. And so the probability that this function is asking for is what is our alpha value. So if our alpha is 0.05, we put in 0.05. And then we put in our total degrees of freedom from the whole experiment, which is this plus this. So we can just throw that in parentheses, this plus this, which of course is 28. And you could just shortcut and put it in that way if you wanted to. So that's our critical value, it's 2.048. And our t-statistic is 1.43. So we did not reach our critical value. Therefore, our results are not significant. Now, there's one more thing we can check, and we can check our p-value. So the p-value represents the probability that we would get this number if there were no effect of our experiment. All right, so the built-in function that we can use to test this is called t-dist. Student's t-distribution, and it's going to ask us for 3 parameters. So it wants the x. Now x in this case is our t-statistic. The degrees of freedom is our total degrees of freedom. So again, we're going to have to add these. Now you might be thinking you might want to add a cell in somewhere that totals these up that you can use in other places. Word to the wise. So we'll add our degrees of freedom. And then the last parameter it's asking for is the number of tails. In this case, we're going to use 2 tails. You may want to use 1 tail, but make sure you understand the difference in them. Okay, now that gives us our p-value, 0.16. Now what that means is there's a 16% probability that any random sample that you make from this population is going to be higher than our t-value. So therefore, we cannot reject our null. Now, if that p-value went lower, let's say that p-value was really low, like 0.001, all right, that would be 1/10 of 1% probability that we would get a higher value. So in other words, as this t-statistic increases, the probability that we could accidentally randomly sample higher than that gets lower. So in the end, when we write up a report, we're going to include our t-statistic, and we're also going to include the p-value. And because that p-value is so high, we're going to reject our alternative hypothesis. We're going to stick with our null hypothesis. All right, so I think that's everything you need to work your way through a t-test by hand and learn some spreadsheet skills along the way. In our next video, we have 4 groups of flies, and we're going to do something called a 2-factor ANOVA, which is like this, like a t-test, but with more dimensions or on steroids or whatever. Stay tuned.